Thanks, Luca. Hello, my name is Lydia Duncan,
I'm Jade Abraham.
and today we're going to be talking to you about Python interoperability.
So what is Python interoperability? For a really long time, you could call Chapel from Python. So you could compile Chapel to a shared library and load it from Python. And that's how many Python libraries work. But in this case, Python is the driver here. Um, but we want to put Chapel in the driver's seat. We want Chapel calling Python. So we're going to flip this around and we're going to call Chapel from Python. And we'll go through a couple of examples, how this all fits together, and some next steps for this. And the question we maybe get asked a lot is, Python isn't high performance. Why would you want to do this? And probably the biggest answer is dynamic execution. You can completely change your program without needing to recompile it and reinvoke the slow Chapel compiler, which we've heard many complaints about today. And you can also embed a full-fledged interpreter in your application and do all kinds of dynamic fun things and lots of funky dynamic things. And you also get really nice access to lots of easy to use libraries, especially AI libraries. So let's look at some examples of all of this. This is kind of the motivating example that led to this library being created. I have some Chapel function that I've called square here, and I want to apply it to a array. I want to, for each element in the array, call this function, update the array. And just to walk you through what this code is doing here real quick, I'm creating a block distributed array here. It only has 16 elements, but it's distributed across however many locales I happen to run this program on. And then I'll go ahead and for each element in the array, I will call square. And square will be called on the proper locale in a distributed and parallel fashion. So using multiple cores and multiple nodes. This is great. If you've written Chapel code, this probably makes awesome sense to you. But what happens when you want to change square at runtime and you don't want to change the definition of what square is? So question is, how do we make this dynamic? And I'm going to show you. So this is kind of the first step in making it dynamic. The first thing we'll do is we'll replace our Chapel definition with a Python equivalent function. So now I've got this Python function embedded as a string in Chapel code. And then I have this little widget here that I've called func per locale. And it's going to handle all the bookkeeping that needs to be done to load up a Python interpreter and call Python. This is going to be instantiated once per locale and only once per locale. And then I've got this cool little wrapper here, which is going to, create a new anonymous Python module from that string and get a handle to the inner Python object called square. And it's going to set it up so that we can just use this object. And then we're not going to quite use that same magic for all, but we are still going to get explicit distributed computation using the co for all. Inside the co for all, we'll create that func per locale. And this is going to give us distributed computation, but not quite parallel. We'll discuss why it's not parallel in a little bit. Thank you, Python and the GIL. But we can call f like any normal function. So you just call f, and just like before, instead of calling square, we're calling f. But now we can kind of tweak Python code. And the one extra thing here is we get back a Python value. So we need to explicitly say, no, I want a Chapel value. Give me the integer and cast it back out. So that's great. But I still can't change this at runtime. We're using Python, but I can't change it. So to change it at runtime, I've replaced the embedded code with some configuration constants, and I pulled out that code to a separate file. And now I've tweaked a couple of lines, and instead of creating a module, I import it. But now I have this separate file, and when I compile my Chapel code, I can just change this file and then rerun my program, and things will be changed. So the behavior is completely editable at runtime. I can call different functions in this file. I can write new functions in this file, or I can call any Python file that I want. So for example, I can just say, call this numpy.negative function. And that all works wonderfully. And I will now hand it off to Lydia to show a more tightly knitted example.
Thanks, Jade. So if you could go on to the next slide, please. So Jade's shown you how to call out to a Python file from Chapel code. This next example is going to intermingle Python and Chapel calls together using Parquet to demonstrate a variety of features. We've listed them here, but we're not going to go through the list now. We're also not going to focus on Parquet details explicitly. Instead, we'll be talking about the features that they exemplify. Next slide, please. So we'll start by importing the Parquet module from PyArrow, using that module to call a function inside it to get our Parquet file. Then we'll use get to access the fields of the file to get the columns. This will return us a Python type, which we can cast to a Chapel list of strings. Next slide, please. This snippet, click, creates an array of Chapel lists storing ambiguously typed Python instances. Click. We then iterate over the Python Parquet file using this iterbatches call directly using normal Chapel iteration. Click. We'll use our Chapel list of column strings from the previous slide to get the relevant column chunk from the Parquet file and store it into the Chapel list of Python types at the irrelevant array index. Next slide, please. So this section of code iterates over the columns again to determine the sum. We've got another cast from a Python type on the top line, this time to a Chapel int. Click. These lines called out here will together get a string description of the Python type stored in the field. This is important because Python can store mixed types in its data structures, while native Chapel cannot do that. It wants to be a little bit more restrictive. Click. We will then iterate over the Chapel list of string columns again. Click. And within the body of the loop, we need to account for Python's dynamic type, but, click, we can take advantage of Chapel's generic functionality to still call the same function. This function will use numpy to gather all the chunks together into a single array, which we can then sum using Chapel reductions. Next slide, please. Finally, we'll dive into that function that I mentioned. Click. We will create an array of our expected element type and size, traverse the Chapel list of Python values passed into the function. Click. We'll then call the toNumpy method on the Python type to get a reference to a numpy array. We've specified an explicit Python type to return here instead of the generic value type so that we can, click, call the array method, which will return a reference. But because we are storing the result into a portion of a Chapel array, a copy will then occur. Next slide. So we're going to briefly talk about the Python library implementation. Next, please. So this library serves to embed the Python interpreter into the Chapel application. Python has this notion of the GIL, a global interpreter lock, to prevent data races, and that is managed by the library under the covers. The library also handles reference counting for Python types, so that they stay alive and are cleaned up as appropriate. For productivity, the library accepts both Chapel and Python types as arguments, and will convert as needed to the appropriate Python type. Users can also register their types, enabling the library to know how to represent them to Python. Python objects will be referenced instead of copied, which can give a performance boost, especially for passing the same object back and forth to Python. Most of the implementation is Chapel code, relying on Chapel's C interoperability to use Python's C API when possible, or defining additional wrappers when necessary. The latter were only used rarely, meaning that the strategy could be feasible for other interpreted languages like Julia or R. As you guys saw yesterday, there's a lot of excitement around potentially using Julia with Chapel, and I believe Jade has actually tried some experiments along this line in the last 24 hours, so maybe they'll talk a little bit about that. Next slide, please.
So we'll kind of wrap this up with some future looking of what's kind of next for this. So first thing is to talk about performance. Even though Python is not a high performance language, we can still get better performance when we're using it, especially with multi-threaded parallel processing. We mentioned the GIL. Python is inherently single-threaded because of this GIL, and newer Pythons are starting to look towards removing this GIL. And when they do that, it will essentially give us free performance. So we don't have to do any work, which is great. And the other thing that is some active work being done right now is improving Chapel's function pointer support. This is to get better dynamic loading with C libraries, but it's also going to give even tighter integration with Python JIT libraries like numpy. And so this will give the dynamic execution that we want from Python, but actual good performance. And everybody loves their super powerful GPUs. And with Chapel's GPU support, we'd like to be able to call Python GPU functions that was written in a kernel in something like CuPy, especially with all the intention that's getting focused on Python and machine learning. And there are some sharp edges to this library that we'd really like to shave off. If you have multiple libraries that are all creating an interpreter, it's going to fall over. It's not that bad, but it's a sharp edge in the language. And there are some libraries that can not work as well. And all of this is done in Chapel module code, like Lydia said, which is awesome. But maybe there's ways that we can make the syntax a little bit more native feeling for Chapel programmers by integrating this into the compiler. And like Lydia said, there's the potential for other interpreted languages. And I did use this as a blueprint and all the experiences learned from this to write a brief little version, which is doing the exact same thing that we showed here, but with Julia. So it is totally possible to extend this to other languages like Julia. So that's awesome. That is the end of our slides. We will happily take questions now. Thank you all very much.
Yeah, thank you for the presentation. Let's thank the speakers with a virtual round of applause. Are there any questions from the audience? Yeah, Michael.
Yeah, I have a question mostly for Lydia. You showed an example with parquet reading. How does that perform? Is it performing well, or we don't know yet? Or
Don't think we've studied that for performance yet.
I think
Jade, do you remember?
It'd be interesting to compare it with the Arcuda parquet reading just to see what you got.
I suspect it won't be very good, but it would be interesting to see what the difference is.
Yes, thanks.
Yeah, good question.
Are there more questions? Yeah, someone raised their hand. Yeah, Amanda, go ahead.
Great talk. I really appreciate it. I'm excited about this feature because I work on the Arcuda project, and we really Arcuda is a pandas-like what's the word? I don't know. It's pandas-like, and we'd really like to integrate with other tools. So I think this is going to be really helpful for that. My question is similar to Michael's, that do you have any plans for performance testing? Because we know it's probably going to be slower, but the question is it still like usably slow, or is it going to be a lot slower? So that's my question.
I would expect the performance to be the same as using the same library in Python. If not, that's my expectation for it. Jade, do you have better sense on that?
It really depends on the Python code that you're running. I'll jump way back to the example here, where if I was, I can call numpy functions that are Python functions that are actually implemented in C. So there's like a little bit of overhead to get through Python into C, but you're still calling, optimized code at the end of it. So I would expect it to be decent. Maybe not as good as just pure native code, but it's better than nothing. And like we mentioned, there's a lot of opportunities for improvement here, and doing some actual performance studies of this as well.
Thanks.